All right, so I'm going to take you through a couple of things with ionic bonding and then covalent bonding and diagramming both of them for your packets. So you need your packets with you, and then I'll take you through a few review items, and then I kind of guide you through some of the packet work so that it can help you be able to answer the questions. All right, so looking at ionic bonding, one thing about ionic bonding is it always involves a metal and a non-metal, right? So this was established early on that we have a metal, non-metal, sometimes abbreviated M and N. Sodium is a metal, whereas chlorine is a non-metal. What happens here is that sodium is going to lose its electron because chlorine wants it more than sodium does. And so there's going to be like a tug of war match over this electron, right? So you can see in this valence shell, sodium only has one valence electron, whereas chlorine has 2, 4, 6, and 7, right? Now, chlorine wants to have 8, and so what it's going to do is it's going to steal this one from sodium, and so it just picks this up and it moves it over here. What that does is it now makes it so sodium has 11 protons and 2, 4, 6, 8, 10 10 electrons, excuse me. So 11 protons, 10 electrons gives us an imbalance of +1. Chlorine having 17 protons and 2 plus 8 plus 8, 2, 8, and 8 is 18 electrons and 17 protons for an imbalance of -1, right? So this is where ionic bonding comes from, right? We have two ions. Since they have a positive and a negative charge, they are attracted to each other, and we have a bond, right? So this is how this is diagrammed using the Bohr model. We're going to diagram this using shell diagrams as well as Lewis dot diagrams. So this is more complicated than what we're going to be diagramming in our section, and I'll go over that with you right now, specifically with sodium and chlorine as our examples. Okay, so with sodium and chloride, very similar to what we had before, but just not with dots, instead with numbers and letters. We have sodium and chlorine. We have both nuclei, 11 protons, 12 neutrons for sodium, 17 protons, 18 neutrons for chlorine. Okay, with the levels of 2, 8, and 1 electron for sodium, 2, 8, and 7 for chlorine. All right, how do we diagram this? This is what we look at in the before. So I'm going to skip ahead and show you what this would look like on your notes. All right. So here we go. No, that's not what I want it to look like. Okay. So within shell diagrams, it says do the crisscross first. That's important here, that we need to do the crisscross method first to make sure that we have the right number. So since that's what it told us to do, we're going to do that. So I do Na, which is +1, Cl, which is -1. Since it's in a 1-to-1 ratio, I know that I just need one of each. So my before bonding for sodium is going to be I have 11 protons I'm sorry. Apparently I am still drawing those 11 protons, 12 neutrons, okay, and 2, 8, and 1. Reminder, this is number 18 on your packet, so please follow along with number 18 on your packet right now. And when we have 17 protons and 18 neutrons for chlorine, 2, 8, and 7. Here's how we diagram this. Sodium is going to steal this from, chlorine is going to steal this from sodium. So this electron is going to go from sodium to chlorine, right? And it's going to move from the left to the right. The way that we show electrons moving is that we circle it and we draw a curved arrow. It's just how in chemistry we do that. Okay, so what does that look like for the after bonding? Well, it's basically most of the same stuff. Just put over here. Now, I get to cheat because I have the tech. Okay, now what's going to happen here is the 7, having gained 1 electron, right? Do 7 plus 1, and that's going to be 8. So I have 8 electrons over here. Now, why did this happen? This happened because sodium now has 8 electrons in its valence shell. Chlorine has 8 valence in its shell. Both are happy, and everybody is stable now. What it also does is it gives sodium a +1 charge and a chloride a -1 charge. That creates a bond between these ions because of the positive and the negative charge. Okay, so that's how we diagram the sodium chloride bond forming in shell diagrams. We're now going to look at Lewis dot diagrams. Okay, so I'll come back to this in just a moment. All right. Using this diagram, what we're going to look at here is very similar, but as mentioned before, Lewis diagram is much easier to do all of these diagrammings than shell diagrams. So much like we saw here with the transfer of electron there, right? What we're going to see is the transfer of electron, but through a much simpler method, right? What we're going to see is that. Right? So the diagram that we're going to look at after that is going to look like this. Right, so we're going to have Na. It's going to be +1 because it just lost an electron. And we're going to have Cl because it just gained 1 electron. It is going to have a -1 charge. There. That's how we diagram this using Lewis, right? So this is the Lewis diagram. Much, much, much easier. I'll show you what it should look like over here as well. So again, over here, we have Na and we have Cl. Notice that it says for us to, again, do the crisscross first. We're going to do that again just to make sure that we understand that we have to do this every single time. Na is +1, Cl is -1. Because they cancel out, or we do the crisscross method, we end up with NaCl, 1 of each. Now, how we diagram this, though, is sodium is over here. Chlorine has 1, 2, 3, 4, 5, 6, 7 valence electrons, what happens here is that sodium will lose it to chlorine. That's the before bonding. The after bonding is sodium having now lost one electron becomes Na+1. Cl having just gained one electron now has 1, 2, 3, 4, 5, 6, 7, 8 electrons. And because it has gained one electron, it is -1. So when you look at both of these examples, they are identical in the process, but they're different in how we represent them. This is the difference between Lewis dot diagram and shell diagrams. Lewis diagrams are a lot easier to do, whereas shell diagrams, there's a lot more information that it tells us. So they're both useful, but we like doing the Lewis diagrams a lot more. All right. Now, the reason we do the crisscross is for cases like this. So aluminum, if you look at a periodic table, aluminum is in group 3A. Now, what that means for us is since it's in group 3A, it's going to form a 3+ charge ion. And chloride, which is in group 7A, it's going to form a 1- ion. Now we can say +1, -1, +3, -3. It doesn't really matter. So since we should just be consistent, we'll say +3. And here we'll also say -1 rather than 1-. Depending on the chemist that you're talking to, they might refer to them in either way. Okay. So what we need to do, though, is we need to first, as we said before, we have to do the crisscross method. So we do the crisscross method here. And we do aluminum +3, chloride -1. Crisscross method takes the 3 down here, brings the 1 down here. We're left with the formula AlCl3. What that means is that my chlorine, I have to have how many of them? 3. And so I'm going to put in another one and another one. All right. So what's going to happen here is as same as before. Chlorine still needs 1 more. Aluminum has 3 valence electrons, right? It's got 3 valence electrons, and it doesn't really hold on to them very strongly, but more strongly than sodium or potassium. And that's why sodium and potassium are actually more reactive, because they want to get rid of those electrons more quickly than aluminum does. But aluminum's going to lose this electron to chlorine. It's going to lose this one to a different chlorine. It's going to lose this one here. All right, so here's what it's going to look like in diagram form, like this. That's what it's going to look like in diagram form. This would be our before drawing, right? So again, I'm gonna we're actually not going to do this on the paper, but you can add this to your notes, etc. So this would be the before. What I'm going to do is I'm just going to cheat because I can and I have the technology. I'm just going to copy the whole thing. And I'm going to draw the after diagram just underneath. Okay. All right. So what this is going to look like for the after is, let me just simplify. That's not simplifying. Let me just simplify things here a little bit by getting rid of that. And I'll draw in my aluminum, which has now lost 3 electrons, which have gone here, here, and here. And aluminum has become +3, and each of the chlorines has become a -1 chloride ion right there. And now they are electromagnetically attracted because they are positive and negative. There are 3 positives in aluminum, and there are 3 negatives in each, or in a total of the 3 -1 chlorides, right? So this would be my before and after for diagramming my ionic bonds for aluminum chloride. Again, notice that it is a metal and non-metal bonding. And so when you add these to your notes, make sure that you remember that it is ionic because it is metal, non-metal. All right, now taking a look later, down to number 19, it says what are covalent bonds. Now, much like ionic bonds are between a metal and a non-metal, okay, covalent bonds we have said are between, it's too thick. Covalent bonds are between a non-metal and a non-metal. For almost all of the cases, it's going to be a non-metal, non-metal. Sometimes there may be a metalloid involved, but usually it's a non-metal and a non-metal. Okay. Now, the difference between an ionic bond and a covalent bond is that covalent bonds share valence electrons rather than seeing a transfer of electrons, right? And with them sharing, there are no charges. There are no charges to worry about. There are no ions. That's why they're not called ionic bonds, because if there were ions, we would call them ionic bonds, right? Now, a difference in covalent bonds is this next number 20. We have to worry about prefixes. It's just the rules of chemistry that when naming ionic bonds, we don't use prefixes. However, with covalent compounds, we do use prefixes. And so really easy here. They're in order, but the prefixes are given on the left, and the meanings I'm going to write in here. Just copy them down and put them into your own notes as follows. All right, so mono means 1. You can think about the monorail or a monocle. Di means 2. Okay. Tricycle means 3. Tetra means 4, like the game Tetris. Each of the shapes has 4 squares in each one of those, right? Right, each one of those has 4 shapes. Penta means 5. Hexa means 6. Hepta means 7. Octa means 8. Nona means 9. And deca means 10. So the rules for naming covalent compounds are as follows. Again, please just write these down as you are following along in your notes. If it needs to be paused, feel free to pause at any time. So the rules for naming covalent compounds are a little bit different than the ionic compounds. For naming, you're always going to have 2 nonmetals, right? It's going to be nonmetal, nonmetal. I guess we'll call it nonmetal number 1 and nonmetal number 2. So for example, in CO2, the first nonmetal, or we'll just call it element, the first element only receives or only gets a prefix if there is more than one of them. So again, in CO2 as my example, the C is carbon, but there's only one of them, so it's just carbon. Right. For the second element, it always, and please underline that, it always gets a prefix, even if it's just one. Always gets a prefix, and the suffix changes to IDE. Just like we did for the ionic compounds, right? Everything ended in "ide," right? So sodium chloride, lithium oxide, everything, the first element, metal, the name didn't change at all. For covalent, however, if there is more than one of the first element, we do use a prefix, right? One of these mono, di, tri, tetra, penta, hexa, hepta, octa, nona, or deca, but only if there's more than one, and even then we don't change the ending. So again, using our CO2 as an example, C is the first and it's just carbon. Whereas in O2, there are two of them, meaning di, and then we change the suffix to IDE, so it's dioxide, carbon dioxide, CO2. So the name of carbon dioxide tells us how many of each of these elements there are in the compound. All right. All right. So this next part for diagramming covalent bonds, I'll actually be teaching this at another time. I think you have enough for the diagramming of ionic bonds, as well as doing the naming of both ionic and covalent bonds, or ionic or covalent compounds, to give you enough to work on for today. So I'm going to kind of guide you through this next part. So over here on the left side of, I guess it's found on your next page, the writing of the formulas or determining of the names of each of these. Now, one thing that you have to do here is determine whether it is ionic or C covalent. How do you determine that? Well, you simply just look at whether or not it is a metal, non-metal. Now, calcium, being on the left side of the periodic table, is a metal. Phosphide is a non-metal. Because it is metal, non-metal, it is going to be ionic. And so we put an I here. That one's already done for you, right? So looking at the next one, aluminum sulfide, aluminum also metal, sulfide non-metal. So we put an I here for ionic. Now, one thing that you need to do for every single one of the ionic compounds here, ionics always need to have the crisscross method done. We must do the crisscross method. And so for that, we'll just do these examples, do these first couple examples together, and then I'll let you do the rest of them on your own. I'll be sharing an answer key on this with you so that you know if you've done it correctly or not. All right, so calcium phosphide. Calcium is in group 2A, right? It's in group 2A, so it is going to be calcium plus 2. Phosphide is in group 5A, and that becomes a minus 3. So it's Ca plus 2, P minus 3. We do the crisscross method as always, and we end up with Ca3, P 2, which makes sense because I now have 3 of these at +2 charge each, 2 of these at -3. So overall it's +6 -6, which balances out. So over here, I have Ca3P2 as calcium phosphide. Aluminum sulfide, I do the same thing. Aluminum is in group 3A, so it's +3. Sulfide is sulfur, and it's in group 6A, so it's -2. Do the crisscross method again. The 3 comes down, the 2 comes down, and I'm left with Al2S3 for my formula, and that's what goes here, Al2S3. So anytime you see an ionic, you need to do the crisscross. You must do the crisscross method if it's ionic. Now, anytime you see a prefix, you can rest assured that it is going to be a nonmetal covalent. Since it's nonmetal, we know that it's covalent. Since it's covalent, we do not have any charges involved, right? There's no crisscross method. There's no charges, no ions, no crisscross. So how do we determine the formula? We just look at the name. Sulfur, are there any prefixes? Since there's not a prefix for sulfur, we just write S. Dioxide, di meaning 2, oxide meaning O, so we finish that off with O2 to represent the 2, right? The 2 from the dioxide, and sulfur just being 1. So sulfur dioxide is SO2. And for the next 10 or so of these, you just determine whether it's metal, nonmetal, or nonmetal, nonmetal, metal, nonmetal. Determine if it's ionic or covalent, or ionic or covalent. And then you determine the formula by doing the crisscross method for ionic, or just looking at the prefixes if it's covalent. On the right side of the paper, you do the opposite, right? So here, sometimes it's a little bit trickier, sometimes it's a little bit easier, but you look at these two elements, you got to remember the formula, or excuse me, you have to remember the symbols. Use a periodic table. You should have one with you. You should definitely have one. Don't get carbon and calcium confused, right? Anything that looks like a capital letter I, make sure it's a capital letter I and not a lowercase l. Like here, aluminum, Al. And here, this one's tough. It is ICl2, right? It's not ICI. Anyway, first thing you need to do is you need to determine whether it is a metal nonmetal or nonmetal nonmetal, right? So since carbon is a nonmetal, fluoride is a nonmetal, this is going to be covalent. Since it's covalent, I need to use my prefixes. Right? I need to use my prefixes. So CF4, C, since there's only one of them, is just carbon. And F is fluoride, but there are 4 of them. And so the prefix for 4 is tetra. And so CF4 is carbon tetrafluoride. AlBr3, since aluminum is a metal and bromide is a nonmetal, it's a metal nonmetal. We know this is ionic. And since this is ionic, there are no prefixes. And since there are no prefixes, you simply name the metal first and then the nonmetal with an IDE ending. So Al is aluminum or aluminium, and Br is bromine, but it's bromide because the ending changes to IDE. And you do that for the next 10 or 11, right here. And again, I'll be sharing a key with you so that you know if you did it right. And then you can see what you can do on the last few pages for diagramming the ionic bonds if there's time in class after having watched all of this. Anyway, good luck to you. Remember that this is going to be posted in your Google Classroom as well as shared with you by your teacher, your substitute today. So just let me know if you have any questions, and I'll go over covalent bonding with you guys later, at a later time. All right, thanks a lot.